Hello, everyone, and thank you for joining our session. Today, we would like you to introduce you to infrastructure programming. If you thought that orchestration so far was a headache, we'll try to give you a solution. So my name is Tomek Zawadzki. I'm SPDK core maintainer at Intel. And together with Jarek, we'll be presenting today's presentation.
Hello, my name is Jarek Kogut. I'm working at Intel as the tech lead in the team working on IPU and storage solution. Let's go to the topic. I skipped this disclaimer. Okay. The one of innovation in data center architecture is proposing new class devices in data center, which is places instead of standard NIC in the host connected to data center. One of example of this kind of devices is IPU. What is the IPU and what kind of capabilities they have? Of course, they have capabilities connected to network, and but it's much more. For example, they expose network NVMe capabilities, other storage capabilities. Another important things that they have capabilities of programmable hardware. What does it mean? They have on IPU and DPU devices, we have additional core CPU cores when we are able to run OS and as well CPS additional software. The one of important use case for this class of devices is the storage use cases. Let's discuss quickly these things. Let's try to compare how the storage software looks like for standard NIC and for IPUs. When we talk about the storage software, we think about storage over network. And when we have the standard NIC, the NVMe over initiator software is running on the host CPU. And as well, the NVMe device is exposed by software running on host CPU. In the IPU case, that is completely different situation. On the host side, we have only NVMe PCI driver. NVMe over initiator software is running on IPU. And let me quickly walk through over different use cases when we may be used. The bare metal case, that is the first one, which we discussed earlier. In this case, NVMe PCI device is exposed to host. Standard NVMe device is running on the host. But NVMe over initiator software is running on IPU. The next one is virtualized cloud. In this case, the IPU exposed to host two kinds of devices. That's physical function and virtual function. Virtual function and of course physical function may be directly connected to VM, and VM we again use the standard NVMe over PCI device. In this case, NVMe traffics pass through directly to IPU hardware without any software assistant on the host. And more important things, one additional important things that we can support live migration for these pass-through NVMe devices, because we are able to save NVMe controller state on IPU and then restore this state on the another host and restore VM on this host. We discussed NVMe case, but VirtIO block device we can expose as well to with using IPU device. And for supporting this, we provide abstraction virtual block in SPDK 20.05 release.
All right. Thank you, Eric. I'd like to tackle some of the ideas behind IPUs and what are the advantages of managing storage and what features do storage features on IPU are presented. So first of all, what kind of problem we are solving with IPUs? So in data center, when you configure a host, that means that you have to do every single step of its configuration on the host. If anything changes at a later time, you have to modify the configuration. There's different frameworks for that and ways to set that up. But in general, as you scale up the number of hosts and the size of your data center, that becomes yet another problem to overcome. So the host orchestration itself at a scale is the problem IPU is solving. And it's doing that by separating the workload and infrastructure configuration from each other. As shown on this example, the NVMe driver is the only part that remains on the host. Meanwhile, NVMF configuration is separate from that. But that not only means that it's possible to separate those, but it's possible to add something that either wasn't possible on the host or was there but required some hardware enablement or hardware features. For example, if we talk about crypto and compression, there is different set of accelerators. Not all of them might be enabled on the host originally, but with IPUs, it's possible to, first of all, have those and enable those on case basis. Depending on what's needed on the host, the IPU itself might or might not enable that. And with each generation of IPUs, it's of course possible to offload and some set of operations, and as well as have additional types of offloads as the generations progress. So what kind of features were moved from the host to the IPUs? So let's start off with clarifying that on the IPU itself, there has to be some kind of storage application running that actually manages and presents certain devices to the host. In this case, it's an SPDK-based storage application. So key point here is that, for example, the backends, meaning what's going over to network to some remote target, can be interchangeable. Right now, if you're using SPDK, you can configure that using NVMF, iSCSI, but SPDK being flexible, it's possible to have more in the future. Another benefit is that you're getting the features of management of the connections themselves. In NVMF case, that's specifically multipath and discovery of remote targets. That's simply by virtue of having SPDK running on IPU enables that. Another is thanks to having this control over the interfaces, over the devices that are connected over the network and then presented to the host, it's possible to deliver set quality of service on per device basis as needed. Another important part of all of this is as well what's happening within the application itself. The hardware that's being visible on the host is programmable, not only in means of orchestration, but as well as what components or what features are enabled in the application itself. In SPDK's case, that means that the layer in between, the BDEF layer, allows us to first connect over the network to a set device, then build another BDEF on top of that. For example, the aforementioned crypto or compress BDEVs that are available in SPDK. And only then those are later exposed to the host. But that doesn't end there. SPDK's BDEVs can opt to use certain accelerations using acceleration framework library present in SPDK that can improve certain set of operations. Going even further, anyone interested enough can add their own BDEV, realizing functions that are necessary for their business. And now, together we'll go over some of the target agnostic frameworks that enable storage infrastructure programming, starting with SPDK. SPDK, Storage Performance Development Kit, is a set of user space libraries, drivers, applications, and different set of tools. The project is community driven. The license is BSD, so one of the most permissive ones. And the whole stack and each of its component is optimized for leading edge storage solutions, which is exactly what we're presenting here now. The components included are ones shown on the presentation, but many, many more to come or added since this slide was originally created. Today, we are focusing on some of those, which are specifically NVMe and NVMF, as well as mentioning the BDEV services. But as you can see, there's quite a few more from that, as well as the acceleration framework previously mentioned. And then, let's say that the SPDK application is ready to go, set up in whatever configuration is required, but actual orchestration of it is a separate part. This is what Storage Management Agent is doing. This is a separate service running on an IPU, which manages the SPDK application. By design, it's intended to be generic enough so that the operations it actually performs when interacting with SPDK storage application is targeting the IPU use case, as well as this allows for it to be adapted to any kind of orchestration framework. During the development, a key way for us to prove out the design, for example, was to make sure that the APIs align somewhat with the Kubernetes CSA APIs. So SPDK is, SMA in SPDK is a very fresh addition, currently supporting APIs to present NVMe, VirtualBlock to the host, and connection to remote NVMF volumes. There's more features coming in SPDK 2009 and further, so please keep your eye out for that. And giving mic back to Jarek.
So, as Tomek mentioned, SPDK is the key framework for us for running on IPU storage software stack. I would like to bring to your attention to other activities which may be important in driving any work related to infrastructure, programmability, and the storage. First, I would like to introduce IPDK. It is an infrastructure programmer development kit, and that is community-driven effort, which try to demonstrate way of programming infrastructure on different kind of devices like CPU, IPU, DPU, or network switch. They try to demonstrate receipt on the virtual infrastructure devices and then try to prove this kind of proposed receipt working on real devices like IPU. Another activity which I would like to bring into your attention is OPI, Open Programmable Infrastructure, that is effort established under as the Linux Foundation project, and the focus OPI is similar like IPDK, but they try to the effort tried to drive APIs, which will be important for devices like IPU. And what's happened up to this moment in OPI in IPDK for storage topic? The first IPDK release happens in July this year. In this release, we provide a receipt for storage use cases. When the host interface is VirtualBlock, on IPU is running SPDK application with SMA API, which Tomek mentioned earlier. The remote target is NVMe over TCP target. In OPI area, that is ongoing discussions start about how this general API for infrastructure for storage should looks like. That I provide here the link to when this kind of activities is ongoing. And what's happened in OPI and IPDK happens in the future related to storage topic. And the first thing is that we want to first in IPDK we demonstrate VirtualBlock. We want to extend this to exposing NVMe. We want to expose more use cases. We now expose bare metal use case, but we consider virtualization and containers. And we want to work on defining API important for managing infrastructure devices in the common way, not device specific, but common way. And we are focusing on SPDK SMA API extension and on OPI extension. And what is important for us? That is completely new activities, and that is for new class devices, and that is important to join and invite everyone to participating in defining new road for this kind of devices and this kind of software. Let's go to summary, and that is two aspects. One aspect is the hardware. That is new class of hardware brings to us possibility to divide to workload to separate workload, infrastructure workload and customer workload to run on separate cores. And this kind of hardware capabilities and allows us to develop new class of software which help with this exactly problem when you have this with standard when everything is running on the host CPU. That is everything what we want to discuss with you today. Thank you for your patience.
Thank you for joining us on this presentation, and we hope to talk with you on SPDK, IPDK, or OPI channels that are open for everyone. Thank you.
Thank you.